Our speaker tonight is RTB Senior Research Scholar, Dr. Jeff Zweerink. Jeff has a PhD in astrophysics with a focus on gamma rays from Iowa State University. He's the author of more than 30 academic papers, and he's written the RTB books, Escaping the Beginning, Confronting Challenges to the Universe's Origin, Is There Life Out There? And Who's Afraid of the Multiverse? Plus, he's co-authored the book, Building Bridges, Presentations on RTB's Testable Creation Model. He and his wife, Lisa, have 5 children, and they live in Southern California. And he is currently employed at UCLA, and he's going to tell us a little bit of something about that because he's talking from an office at UCLA. So please join me in welcoming Jeff.
Well, hi, Kirby. Thanks for the opportunity to be here. Yeah, as you can see, I got a few physics equations on the board behind me, and I can't claim any credit for these because I'm actually in the office of the lab right next door to mine. This is the lab they're working on here, or the research they're working on here is building the next generation of gamma ray telescope that will enable us to do wide field surveys of the sky for gamma ray sources instead of the more traditional where you point at a source and take data there and have to go all over the sky to map it out. And so, enable you to be able to get data more quickly on more transient sources and just be able to have better sky coverage. But what I work on while I'm over here is a related project. It's in the field of high energy astrophysics, is a balloon experiment where we are looking to find particles that if we find some small set of these particles, and I'm talking small like 4, 5, 6 of them, it will greatly inform us as to what in the world dark matter is. We know that dark matter is out there because we can measure its gravitational effects, but we cannot measure what it is yet. And we think it's a particle of some sort. The question is, what kind of particle is it? And one of the prevailing ideas is that the dark matter is a particular type of supersymmetric particle. And it turns out, without going into all the physics behind it, that for every particle, electrons, quarks, there are corresponding supersymmetric particles that are very heavy, and the lightest one of those heavy particles is stable. And if those things, they happen to have this funny, not unique, but odd property that they're their own antiparticles. So we're sitting in a bath of dark matter particles. Occasionally 2 of them will collide, they'll annihilate into pure energy, and then they can produce some other particles that we can detect, like an antiproton and an antineutron that get together and are moving at a certain velocity. And so we're building a balloon experiment that will fly up and go around Antarctica for 30, 40 days. Hopefully we can do 2 or 3 trips of doing that, and looking for these occasional anti-deuterons that come through our instrument while it's on this balloon experiment. And when we're expecting millions of events, and so we got to filter out all the background events to get down. Actually, we're expecting billions of events now that I think about it. And so we got to filter all those out to find the 4 or 5 or 6 that are actually interesting.
Wow.
And so if we build this, it will be the largest balloon payload ever flown as a scientific instrument. So it's a pretty cool experiment that we get to work on, and have been working on this for a little bit over a decade. We flew our prototype experiment back in 2012, and I'd been working on it for about 3 years before that. So kind of cool thing that I get to do. So, I could talk for a long time about my adventures in high energy astrophysics, but really what I want to do today is to talk about whether the universe has a beginning. And we're going to get into things like different cosmological models and the multiverse, quantum gravity, and how this all plays into that. But to kind of set the stage, I wanted to just give a little bit of a story. And before I give this story, let me see here if I can. I have my screen sharing is disabled. So if you could enable that while I'm telling my story, that would be good. So about 17 years ago, or sorry, about 7 years ago, it was 2014. I was over in London happened to get to share the stage with William Lane Craig at the Unbelievable conference that was hosted by Justin Brierley, because we were talking about origins and the origin of the universe. And I had written a book, Who's Afraid of the Multiverse? I'd been giving talks on evidence that the universe had a beginning to it, particularly even in the context of a multiverse. And so in the midst of the conference, I got to speak out on the main stage and had about a 45-minute to hour session where I got to elucidate what I thought was evidence for the beginning of the universe. And numerous places in there, I made statement, it's like, there's this, but really when you look at it, the bulk of the evidence points towards the universe having a beginning. And there was a fellow, after the session was over, a fellow raised his hand out in the audience, and he asked me a question. It's like, how can you say this? Because there are these many of the quantum gravity models that are out there don't have a beginning. And I didn't quite get his question, and I didn't, I gave a response, but I didn't quite understand what his question was. And so he came up afterwards, and I talked to a number of people, and he waited till the end. And so we had a little bit of time to talk, and he explained his position a little better, and I could understand. And basically what his position was this, that, we know that we don't have a good quantum theory of gravity. We've got general relativity, which is a classical theory. We've got quantum mechanics, which is not a classical theory. And we know that, or we have this pretty strong inclination that when we're dealing with the early universe, we need both general relativity and quantum mechanics, and they don't play well together. And essentially what he was asking is, as we've tried to develop, or as we're looking to develop these theories of quantum gravity, which will apply early in the universe that allow us to address this question, there are many, and he gave me 3 of them at the time, which say, I've got 3 or 4 different quantum gravity models, which say there's no beginning to the universe. And, the part of that engaged me was not just that somebody had come up with a model, but it's like, here's one way of looking at quantum gravity and it says there's no beginning. And here's another way of looking at quantum gravity that's independent of that and it says there's no beginning. And he had 4 or 5 of those around. And if you've listened too much to RTB and Hugh Ross, one of the things that makes a case or a body of evidence stronger if there are multiple lines of reasoning pointing to the same conclusion. And effectively, that's what this fellow was saying, is that I've got multiple lines of evidence that when we delve into quantum gravity, there's no beginning for the universe. And so once I understood that, I sat back and I had to think. It's like, okay, I see what he's saying, and his argument carries quite a bit of weight. And I think it recognizes a profound truth that I think often gets missed in this discussion, which I'll elucidate a little bit later on. And it forced me to step back and rethink and say, okay, is it still legitimate for me to make the claim that the evidence points towards a beginning to the universe? And so in order to kind of walk you through some of the journey that I had there, and I'll give you the short answer. Yes, I still think the evidence points to a beginning. Let me tell you why, and I'm going to share my screen and kind of walk through some of the ideas, or walk through why I think it's reasonable. In fact, I think it's not only reasonable, but best that we look at the universe as though it had a beginning. And to start with that, where I'll start is, ask the question, did the universe begin? And I'll talk about why we think it did. And then after I get done with that, I'm going to talk about why it may not, and then how we deal with that. And to start to lay the foundation of why we think the universe had a beginning, need to go back about 120 years ago to the start of the 1900s, actually late 1800s. And as Einstein was surveying the scientific landscape, and many others noticed this and recognized it as well. In fact, I didn't realize the implications of this statement when I heard it in my undergraduate physics classes, is that when you do things with Newton's gravity, or Newtonian mechanics, things behave a certain way as you go faster and slower. And it's the way we would expect that if you're driving down the road and you throw a snowball outside of your car, even though you may only throw the snowball at about 10 miles an hour, if your car is going 30 or 40 miles an hour, when it hits the sign, it makes a sound very loud like it hit at about 50 miles an hour. Not that I would know anything about that, but the reason why is because when the velocity of the car and the velocity of what I throw add together. And that's the way Newtonian mechanics works. Well, if you go look at electromagnetism, which was the other known force at the time, it turns out that it behaves very differently, because if you're traveling along on a flashlight that's going the speed of light and you turn the flashlight on, you'd naively think, if I were sitting there looking at it from the side, that the photons coming out of the flashlight would be moving at 2 times the speed of light. Well, it turns out that for electromagnetism to work, photons always move at the speed of light. And so all that to say is that as you move through the universe, Newtonian dynamics and electromagnetism gave different results. And what that meant is that as you're moving through the universe, the laws of physics vary in how they look. And that philosophical problem bothered Albert Einstein tremendously. Bothered other people, but it bothered Einstein enough that he wanted to do something about it. And so what he did is set about philosophically, or starting from this philosophical presupposition that the laws of physics should not change depending on how you're moving or where you're located. He built a physical theory of the universe, particularly gravity, where that was the case. And in his doing that, that's where he formulated general and special relativity, his theories of general and special theory of relativity. And those theories specifically codify the idea that the laws of physics don't depend on location or motion. Interestingly, just as a side point, although it's not too much of a side point, the idea that the laws of physics ought to be the same throughout the universe flow very naturally out of a Judeo-Christian worldview, because the laws of physics flow out of how God sustains creation. As far as I can tell, many other worldviews wrestle to make a cogent case of why we should expect the laws of physics to be constant throughout the universe. Why this was a revolutionary theory and how it relates to this discussion of quantum gravity is that as Einstein introduced his general theory of relativity, it dramatically, fundamentally changed how we thought about space and time. Prior to Einstein, space and time were these static quantities, static entities that mass and energy moved around within. Well, the development of general relativity said that space and time can be warped, and the motion of the objects in there actually changed the very fabric of space-time. And it opened up science to investigate this question of, was there a beginning? Because the generic solutions of his equations predicted either an expanding or contracting universe. And so now this question of whether there's a beginning now becomes a scientific question. It just fundamentally changed how we think about that question. And that's the potential that quantum gravity brings in how we think about this question. But this plays into why we think the universe has a beginning, because shortly after that, Einstein had introduced a cosmological constant to get a static universe, because that's what, at the start of the 1900s, people thought the universe was static and eternal and it existed forever. Well, about 15 years after that, Edwin Hubble, taking measurements of redshifts from distant galaxies, was able to make measurements of how far away these galaxies were. In fact, when he first started studying them, they were called island universes. We only now call them galaxies. They were just these fuzzy blobs that we didn't appreciate. But what he found was this: the more distant a galaxy was, the faster it's moving away from us. That is the telltale signature of an expanding universe. So now Einstein has proposed this general theory of relativity, says that space ought to be dynamic, introduces this cosmological constant to get a static and eternal universe. And now, lo and behold, Edwin Hubble comes along and says, the universe is actually expanding. Well, if it's expanding, that seems to point towards a beginning. And let's ask the question, is that really the case? So this is kind of the picture, and I'm going to show this graphic and imagery with the explicit caveat that this is entirely the wrong way to look at the universe. And it's going to reinforce this wrong way of thinking about the universe as though it's some sort of sphere and some sort of center. But I'm going to show it because this is what people thought for a long time, even though it's entirely inaccurate. So the idea is you got this universe that expands out, it grows larger and larger over time, and the stuff the stuff in the universe gets farther and farther apart. Well, fast forward into the 1960s, early 1970s, Stephen Hawking, Roger Penrose, and other people were looking at this saying, hey, wait a second, as we're studying black holes, we run into this interesting phenomena that if you take a bunch of stuff inside a horizon and it collapses down into a black hole, what you end up running into are these places where the space-time trajectories of these particles cross and you get infinities, the laws of physics break down, and that looks a lot like a beginning. And what he was able to do, or Hawking and Penrose were able to do, was apply this scenario that happens inside black holes to the universe as you run time backwards. And what he found is, lo and behold, as long as general relativity holds, and as long as there's enough mass in the universe and that mass energy behaves a certain way, you end up with this singularity theorem that as you run time back in the universe, you inevitably run into this place where the laws of physics break down, and that's a beginning. And so this is kind of the first really strong piece of evidence that the universe does indeed have a beginning. So for most of the 70s, 80s, 90s, and even into the 2000s, this was kind of the context of the discussion. Now, let me tell you why it might not. So before we do that, or to understand why it might not, we need to get a picture of what we think of when we're talking about the universe, and this will allow us to define a multiverse. And so I imagine everybody knows what this object is. It's a moon. And what's funny about, or not funny, what is interesting about the moon is that it's just over 200,000 miles away from us. And if you happen to remember odd numbers like I do, you'll know that the speed of light is 186,000 miles per second, which means that it takes light from the moon just over 1 second to get from the moon to us, which means that we are not seeing the moon as it looks right now. We are seeing the moon as it was just over 1 second ago. So if we move out a little further to the Andromeda Galaxy, it takes light 2.5 million years to get from the Andromeda Galaxy to us, which means we're not seeing the Andromeda Galaxy as it looked today. We're seeing it as it looked 2.5 million years ago. And if we move even further out, we get to the Hubble Ultra Deep Field, which has objects where light has to travel 8, 9, 10, 11 billion years to get to us. Again, we're seeing these objects not as they look today, but as they looked 8, 9, 10, 11 billion years ago. And if we continue to push even further out, the most distant thing that we can see in our universe is the cosmic microwave background radiation. And this has taken almost 14 billion years to traverse from where it was emitted to our location. And if we go back, so the whole point of this is that if we try and go further and further away, eventually we run into this phenomena that because the speed of light is finite, it's very fast, but finite, and because the universe is about 14 billion years old, there is a maximum size or a maximum distance away that we can see things in the universe. And that allows us to define a region that we call the observable universe. And so if I wanted to now kind of loop around and say, all right, this is, we kind of have a better understanding of how our universe works. How does it actually look? Here's a little bit better picture of what it looks. So, if you were to outside and observe, which you can't actually do, boom, just everything's there. And if you go along every now and again and say you were to stop it at one point in time and make a measurement, and then if you'd come back later and stop it again and make the measurements between the same two objects, what you will find is that during that time, things that were closer together didn't move apart as quickly. Things that were further away moved apart faster. That's what Edwin Hubble measured. So we live in this expanding universe. And so if we kind of keep letting time play out here, you know, things expand. And if we kind of step back and get a bigger picture, we can see all the stuff that we can see. And we can see there's the entire observable universe there, but there's a whole lot more stuff out beyond that. And so now that we talk about, we've got this definition of the observable universe, which is a nice unambiguous quantity. We can now talk about what is a multiverse, because the multiverse is just anything beyond the observable universe. That's a really nice definition, and it's one that we can all at least agree on, whether or it's something that can be well specified. So if somebody comes along and says, hey, I want to do this, at least we know by what basis we're making changes to that. Now, the question is, okay, so if we've got our observable universe, which is the most distant reach that light could travel from somewhere to us, and I would say this is an enormous size, because the stuff that is the furthest stuff where light could reach to the Earth in the history of the universe is about 50 billion light years away from us in every direction. So it's an enormous volume, but the multiverse is just anything outside of that. So there could be other stuff that's just a whole lot more of the same stuff. That's kind of the Star Wars universe, that if we were instantaneously transported to the edge of our observable universe, in all likelihood, it would just look a whole lot more like the same stuff. That's a level 1 multiverse, which I find a very uncontroversial idea. You know, I'll kind of explain in a few minutes, but if inflation happened, this is the kind of multiverse we live in. But typically when people are thinking about it, they're not talking about just more of the same stuff. They're talking about other bubbles where the laws of physics might look different, where the speed of light could be faster or slower, or maybe there's no weak nuclear force, or some of the other fundamental constants are different, or the dimensionality of space and time are different. These are the sorts of things, you know, the level 2 multiverse that most people are talking about. And what we'll find is that this level 2 multiverse is usually a generic consequence of inflation happening. And I'll come back to that in a few minutes. Because that now raises the question of, does the multiverse avoid a beginning? You know, when Hawking and Penrose developed these singularity theorems, they're very powerful that say that if general relativity is correct and if energy behaves a certain way, then we end up with a singularity where the laws of physics break down and there's a beginning. But in order for Big Bang cosmology to work, you need to have this inflationary epoch, because without that, we can't explain some of the fundamental features of our universe, not the least of which being the cosmic microwave background radiation. But inflation, the energy that drives inflation violates the condition that Hawking and Penrose's theorem relies on. So if we live in an inflationary universe, the Hawking and Penrose singularity theorem no longer applies to our universe, and so it removes this piece of evidence for a beginning. And the way inflation works is that there's this stuff that just very rapidly inflates. And because it's not in a ground state, it will decay to the ground state in certain places. And where it does, you get universes. So one of these big, you know, yellow or blue or purple regions would be where it decays to a ground, or to a closer to the ground state. You get something like our observable universe and the level 1 multiverse beyond that. But there's all these different regions where that's happening. And it has this unique property that once this process of inflation starts, where inflation goes and it decays to produce universes, once it starts, it never stops. So it goes on forever. Well, people said, well, if it goes on forever, maybe it has been going on forever. And so it gets rid of the beginning. So does the multiverse avoid a beginning? Well, you can go look at people who are investigating this. They recognize these theorems don't hold. And what they were able to show, Arvind Borde, Alan Guth, Alex Vilenkin, these are people who are instrumental in developing our current view of inflation and how it works. In fact, Guth was the one who really got this picture on the map of how it would work and how it would explain our universe. And I'll come to some of the details of that in a few minutes. But what they were able to do is they said, all right, the singularity theorem of Hawking and Penrose no longer applies. But what we can show is that inflationary spacetimes are incomplete in past directions. And that's just fancy terminology for saying that inflationary spacetimes, space on average expands. And so if you run time backwards, eventually you run into a place where things are moving faster than the speed of light, and that's impossible. And so the laws of physics break down and you have a beginning. So does the multiverse avoid a beginning? No. Even inflation must have a beginning. Now, inflation is not the only place that comes into here. And I talked about earlier about how Einstein was looking at reconciling how the electromagnetic and gravitational force worked with one another. Well, in the start of the 1900s, we only knew about those two. We actually know now that there are two other fundamental forces, the strong nuclear and weak nuclear forces. And in the 70s, 60s, 70s, and 80s, what we realized is that even though the electromagnetic and weak nuclear force look very different, one only operates, the weak nuclear force only operates within the confines of the nucleus. Electromagnetic force operates over the entire distance of the universe. What we know is that they're actually the same thing. We just they seem different now because the universe has cooled off enough. And so if the universe heats up and has a higher energy density, these two forces that look very disparate actually become the same thing. And there were actually 5 Nobel Prizes awarded for this work, 2 for the theoretical work that helped develop it, 2 for the experimental work that measured the bosons that mediate these forces, and then a 5th one was awarded because the reason why the reason why the weak nuclear force only works inside the nucleus is that the particles that mediate that are very massive, and so they only work inside the nucleus, whereas a photon can be massless. That's why it can get across the universe. And so Peter Higgs recognized this, and it's predicted there ought to be this Higgs boson because of the way these things separate and the symmetry breaks. And ultimately, when we found the Higgs boson a few years ago, that was awarded a Nobel Prize as well. So, I mean, this effort to unify the electromagnetic and weak nuclear force into the electroweak force actually had a number of Nobel Prizes that came along with it. And so successful was it that we think, all right, hey, maybe the strong nuclear force unifies in there as well. And that's the grand unified theories that people talked about in the 1980s and 90s. And then ultimately, to get the gravitational force in there, you got to get a quantum gravity. Now, part of where this connects to our multiverse idea is that as people were looking at these grand unified theories, there's one feature of these grand unified theories that is at odds with our observations of the universe. And that is primarily that grand unified theories, when the symmetry breaks and the strong nuclear force separates, it should produce a whole bunch of magnetic monopoles. Well, as Alan Guth was looking into how could we do things where you don't get magnetic monopoles, what he realized is that this symmetry breaking could be preceded by this era where there's this stuff that just very rapidly expands, and so it dilutes the magnetic monopoles down below. So the magnetic monopoles form, but then they get diluted below our observational limits. And this mechanism could actually drive inflation and explain why our universe looks so homogeneous in the cosmic microwave background radiation, why it looks so flat. And so this is where inflation really became a theory, not that people thought, oh, that's kind of cool, where this is actually a good description of our universe. And so this is why we have to wrestle with, it's not like inflation was just invented to try and get around the need for a beginning. It's like, as we're solving the problems that we see, or the things that appear to be at odds in our universe, we're forced kind of into this inflationary model, and it actually matches the observations really well at this point. But this idea of unifying the fundamental forces, it is a very successful scientific endeavor, and I would actually argue that it fits very naturally within a Judeo-Christian worldview, because you have this oneness about the fundamental forces that give the diversity of, at low energies, give the diversity of interactions that allow life to happen. And again, that's the sort of thing I would expect from, or it fits very naturally given what I know about the God of the Bible. And so this search for this quantum gravity, you can see why it's important, and now why this fellow came up and said, hey, in quantum gravity, we don't see any, thus far, at least in these models, we don't see any evidence for a beginning. And so maybe what you have in these quantum gravity models, the sorts of things that happen is, if you go back to past eternity, the universe is contracting, it goes through this very tiny phase, but the quantum gravity keeps it from forming a singularity, and it just kind of bounces. And so maybe it's been cycling this way, or maybe it hibernated for a while and then expanded, or maybe you've got these reproducing universes. So there are all these quantum gravity models out there that seem to have a universe that is populated from past eternity to future eternity, and there's no need for a beginning. So that is why it might not have a beginning. So now, what do I do, or how have I wrestled with that, and what did I come to, and why I'm still confident that the universe had a beginning? Well, let me do a couple of things. In the time frame when Einstein first introduced his cosmological constant, or first discovered general relativity, one of the things that people said is maybe the universe is actually oscillating. So it grows very large, gravity causes it to contract, overcomes the expansion, causes it to contract, it collapses, somehow bounces, and it just keeps bouncing back and forth like this. I'm going to pause this because that gets annoying to watch after a while. But effectively, this is a multiverse model. And so the idea is, yes, the universe is expanding. Yes, general relativity governs it, but this in principle could go on forever. Well, it turns out that when you look at this from a thermodynamic considerations, that as it's expanding, the amount of usable energy decreases with each expansion. And so each expansion actually gets larger and larger and larger. And so though it may expand multiple times, you can it's because it gets larger and larger each time, it still extrapolates back to there being a beginning. And so this is a model that seemed to get around a beginning, but when we investigated it more, it didn't. Shortly after that, especially after the discovery of the expanding universe, one of the very popular models was a steady state model. And in this model, the universe is expanding, and as it does so, once the universe expands far enough apart in the void of space, new matter is being created. And so the universe, even while it's expanding, always looks the same. And think about the implications of what's going on there. People were willing to say, you know what, maybe there's something that actually creates new matter in the universe, and that is why our universe is eternal. That's a pretty remarkable thing. And the reason why it was okay is because it's testable. We could go out and test whether this actually works or not. One of the predictions of this model is that whether you're looking nearby or far away, the universe looks the same. Well, when you look at distant parts of the universe, you see a whole lot more quasars than you do in the nearby universe. And ultimately, the cosmic microwave background radiation says in the past, the universe was much hotter than it is today. And so ultimately, this steady state model fell because it didn't match the observations. And so what it occurred to me is that if you go back and look at the last 100, 120 years, you got at the start of the 1900s, the universe was static and eternal, had existed forever. And along comes Einstein and says, wait, general relativity, and that points to a beginning. People say, well, maybe there's a cosmological constant. Maybe the universe oscillates, and so that doesn't have a beginning. Well, no, the cosmological constant doesn't work because the universe is expanding. And okay, well, the steady state, the oscillating universe doesn't work for thermodynamic considerations. Maybe this steady state model is the one that avoids a beginning. Well, we've discovered the cosmic microwave background radiation, which showed that really doesn't line up. And ultimately, these singularity theorems showed that no, the steady state universe that's not a good way to escape the beginning. Well, you fast forward to the 1980s, you got inflation comes along and it's like, no, this will go on forever. Maybe it's gone on forever in the past. You get a multiverse. And so, yeah, our universe may have had a beginning, but there's no beginning overall to things, except there are these BGV theorems which again are singularity theorems, which say the universe has a beginning in the past. And so now, if you look at this, what we have now is saying, all right, quantum gravity, that gets around the beginning, right? Well, as I look back through the 1900s, scientists have proposed many models that say, oh, this gets around the beginning. Oh, this gets around the beginning. The 20th century is littered with models that got around the beginning, only to have further and deeper investigations show that, lo and behold, they don't align with the reality of this universe. And so why I'm convinced the universe had a beginning is like the 20th and 21st centuries are littered with models that avoided a beginning, only to have the universe inevitably push us back to the idea that it began to exist. So I'm going to pause there. I'm going to unshare my screen. And oops, I'm going to throw it open for questions.
So anybody that has a question, Dave Frazier has a question. Dave, go ahead.
Yeah, I'm not sure I understand it correctly, and I'm not a physicist, but when you talked about the observable universe, that was based on the speed of light, and basically that we could only see a radius of 14 billion light years away, because that the light had there had been a beginning 14 billion years away. So if you take away that beginning, doesn't that take away the boundary of the observable universe? Or
well, it's a little bit bigger than that, and you know, you've highlighted a good detail, is that it seems a little bit circular there. And what I will say is this: that if you go much further away from that, what you run into is this era, whether it's a quantum gravity era, whether it's a singularity, whether it's the boundary of our bubble multiverse, you run into this boundary where it's impossible for us to see on the other side. So even so, whether there's time before that or not, from a practical perspective, or at least from a phenomenological perspective, what we see as our universe or our level one multiverse, there's nothing from prior to that that we can actually measure and see inside our universe. And so when I say our observable universe had a beginning 14 billion years ago, that's just another way of saying that whether inflation heated everything up and reset everything, whether it actually had a true beginning, whether there's a bounce or whatever, there's a phenomenological beginning that prevents us from seeing anything before that. So there is a maximum size that we can see that is driven by that phenomenological beginning, no matter what.
okay, thanks.
So I just have a comment on that, or a question. I guess this is sort of a question, because the way I have looked at this is unfortunately the classic way. I guess I'm not supposed to look at it, but it seems like if I look in any direction, I can see around me. I can see about 14 billion. Well, I can't see quite 14 billion light years away, but that defines a sphere around me that has a diameter of 28 billion light years, and but then objects that are transmitting light outside that would add another 14 billion light years on either end. So I think that's where you come up with the 50 billion light years. Is that right, wrong or right?
It's actually so. The reason why you come up with 50 billion light years is you ask, where is the most distant object now that emitted light that I can see here on Earth? And it's actually the cosmic microwave background, or the region that emitted the cosmic microwave background radiation is that most distant place. And what happened was it was much closer to us when it emitted it. But in the 14 billion years it has traversed to the Earth, the universe has expanded. And so the light has been traveling for 14 billion years, but if you were to make a measurement today of how far away is it, the region that emitted the light is actually 50 billion light years away. And so you got to take into account that the universe is dynamic while this is all going on. And beyond that 50 billion light years, things are so far away that they have not, light will not have had time to propagate to the Earth. And additionally, things out at about 50, things out at that region are moving close to the speed of light away from us. And so there, even in practice, there may not be very much beyond there that ever will have time to reach us. And so we may be seeing about the limit of what we will ever see.
I had a question, Jeff.
Yes.
You made a comment about inflation possibly expanding enough and kind of coalescing other universes so that you had multiverses out there due to inflation. But inflation happened after the Big Bang. Aren't the laws of physics already baked in? And so aren't those all multiverse of type 1 rather than type 2?
So that is a common way of looking at inflation, but it is not the way that the cosmologists look at inflation. And one of the reasons why is because if you have a scenario where universe starts, inflation happens, inflation ends, universe continues to grow, you can fundamentally show that that universe will never be as smooth as we see in our universe. And so you cannot, that model has a graceful exit problem that cannot match the cosmic microwave background radiation that we see. And so that was what Guth recognized as the way to get around that, or the way, not the way to get around that, the way to solve that is that rather than a scenario where universe starts, inflation happens, inflation ends, universe continues to expand, the scenario is you get this stuff, it's called a false vacuum. It goes by various names, but you get this stuff, it's called a false vacuum. Whatever produces that that's a separate question. But once it's there, its fundamental one of the fundamental properties of this false vacuum is to expand very rapidly. But it's not in its ground state. So as it expands in places, it will decay down towards the ground state. And where you get those decays, you now have bubble universes that form in those locations. And our universe is in one of those regions that decayed. And so it's much larger, our universe is much larger than we can see, but that, and all of that energy where it decays goes into reheating the universe. And that's why we now see this homogeneous cosmic microwave background radiation with small fluctuations in it. So it's just a very different way of looking at inflation. The idea that universe starts, inflation happens and ends, and then the universe expands is impossible to reconcile with our observation.
So I have a question as well.
Yes.
Did that answer?
Mm-hmm.
Okay. So I have read or heard Hugh Ross say that basically we are in a position in time where we can see tremendously much of the universe, which I understand. But I'm just wondering if we lived 2 billion years later, then we would see 2 billion years worth more, correct? Or even more exponentially, right?
So there's a balance there in that the amount of space we can see will continue to grow as the universe ages. The amount of stuff within that space may actually decrease, and that's what's likely to happen. So the expansion of space is we're living kind of right at a time, and 2 billion years may not really make any difference in this argument. It may actually be like 10 billion years before it's a significant effect, where as the universe grows older, it expands faster and faster. And so eventually stuff that is within our ability to observe now will expand away from us faster than our ability, or than the observable universe is growing. And so at some point in time, the only thing we will see is the stuff that's gravitationally bound to our local supercluster of galaxies. Everything else will have expanded away. So even though we will be able to see farther away, there will be less stuff to see.
So we are in a sweet spot right now.
We are in this odd region where if you ask the question in, like 5 trillion years, how long of a time, or how long is the time span where there's where the matter density of the universe and the space energy density of the universe are similar? It's a relatively small period of time, and we're in the middle of it. And before that, things are not large enough. After that, things are too large, but it's getting diluted. And so we are kind of in a sweet spot, but that sweet spot is 1 billion years or so. So we are in a sweet spot, but don't push it too hard.
Thank you.
Jeff, this is John Yu. I have a question. You said something I think is quite important. This understanding of inflation. Instead of explaining inflation as in a serial way, you said initially there was an inflation, and then when the inflation stops, then bubble universes condense, and we are in one of these bubble universes. Is that the model?
With a little bit of a caveat. So inflation, this stuff that inflates, it just expands very rapidly. There are places in that big sea of inflating stuff where the inflation field will decay towards the ground state and make a bubble. In the process of doing that, the amount of stuff, the amount of new inflationary space is growing so large that even though you've got these bubbles decaying, the amount of stuff that is still expanding and inflating is actually the same or growing over time. So inflation never ends once it starts, which is really kind of mind-boggling.
Inflation never ends once it starts.
Sorry,
does that mean today there's still inflation going on according to that model?
Let me clarify that. Inflation in this false vacuum or that is inflating, that goes on forever. Where it decays to a lower state, inflation stops in that area, in that bubble where it decays. And so we live in one of those bubbles where it decays, and so inflation has ceased in that sense. But in the big picture, inflation just goes on forever.
Wow. So now, did you say that at the time of inflation, the laws of gravity, or the physical laws that we know in our bubble, does not exist? Only once it condenses to a bubble universe, and inside that universe is where the laws of physics exist?
Well, so the way I would say it is, when the universe is very hot and has a very high energy density, all the laws of physics that we see, the electromagnetic force, the weak nuclear force, the strong nuclear force, gravity, those are all unified into a common single force. As the universe cools, that single force separates and breaks into the other forces that we see.
Oh, I see. So that's a theory.
It's a theory that's backed up. I spent a fair bit of time talking about how that happens with the electromagnetic and weak nuclear force. We know that happened. We think it's true of the strong nuclear and gravitational force as well.
Right, but since in our observable universe, we cannot do any experiment outside of our observable universe, there's no way to prove that theory.
Well, what you can do, and the way we were able to show it's true for the electromagnetic and weak force, was we could develop the theory, do the theoretical calculations, and say, if this is true, then there are these particles that we have not detected yet. And if we build a particle accelerator, we ought to see these particles. They're the W and Z bosons and then the Higgs boson. And so we built particle accelerators and we found all those particles. And so that says this was correct. Now, the challenge with the strong nuclear for the grand unified theories and the quantum gravity theories is that the energies are orders of magnitude larger than what we can do in our most powerful particle accelerators. And so what we're hoping for is that maybe there's some phenomena out in space that allows us to do those, or that are kind of performing those experiments for us that we can observe. But that's one of the questions we're asking is, can we do an experiment that allows us to verify that? We can do that with the electromagnetic and weak forces. We can't do that with the strong nuclear force, the grand unified theories, and we can't do it with the quantum gravity theories either. So that's part of why this fellow's argument doesn't carry quite as much weight for me, is that he's saying, all right, this theory of quantum gravity says there's no beginning, and this theory of quantum gravity says there's no beginning. What I don't know is two things. One, which of those theories is correct? We have no idea because we don't have any experimental evidence that would allow us to say, oh, this one matches and that one doesn't. And we won't have that for quite a while is my expectation. Nor do we have, say, all right, so if we can't narrow it down and say this is the right quantum theory of gravity, we also cannot go in and ask the question, generically, do quantum gravity theories predict beginnings or not? There is kind of I don't want to say bias is not quite the right word, but people are prone to look for theories that don't have a beginning, in part because they're physically more interesting because they have the symmetry of not having a beginning. And physicists really like symmetry. The reason we do, the ability we have to make progress in electroweak theory is built on these symmetries. And so symmetries are pretty important. And if you have a beginning, you've broken a symmetry there. So it's an interesting argument. It's not nearly as strong as it sounded at first as I began to think about it more.
So how does, my last question.
Okay.
So how does all of this inflationary tie to the Big Bang, a singular beginning? Where is the singular beginning?
So in inflationary Big Bang cosmology, the singularity is the edge of the bubble where the universe, where the inflation field is decayed. That's the singularity. And there's a question. So I'm trying to figure out how to say this precisely. It's not as though it's a singularity, because inflation doesn't have a singularity there. You can describe the laws of physics growing through there, but that boundary has a practical edge in that information that's outside can't be transmitted in and vice versa. And so it's kind of like an event horizon around a black hole. It's not a singularity there, but there's a fundamental separation between information inside and information outside. And so you need to be careful. We got to be careful about using the term singularity when we're talking to the boundary of that bubble, because that's not really quite the right term.
Okay, thank you.
The singularity that Borde, Guth, and Vilenkin was talking about was looking at the inflationary field as a whole. It says, even if you transform to the edge of our universe, or to the boundary of our universe and beyond, and then keep working with the laws of physics, you still run into a boundary, which is a singularity.
And can I ask,
Randy, go ahead.
okay, yeah. So I have two related questions. One is, just sort of the idea of an observable universe, and sort of its consistency with the speed of light being a constant and other things. So I guess the way I'm picturing it is, you've got a raisin cake, where galaxies and planets are raisins, and it's expanding, and so you couldn't have a ray of light. So basically, the raisin cake can expand at a rate that's sort of faster than the speed of light, because sort of the shape of the fabric of the space-time continuum is changing. But if you had someone on one of the raisins turn on a flashlight and aim at the other, it would be bounded by the speed of light. So that's, I guess, is that a conceptually a reasonable way to think about it?
Yeah, no, you've got the fundamental principles there, and I'll state it a little differently just because I like to rephrase things, is that there's two principles at work. That there's a fundamental tenet of general relativity is that nothing can move through space faster than the speed of light. So the light from these objects has to travel through space, and it's bounded by the speed of light. There is no corresponding limit on how fast space can expand. And so in inflation, space expands much faster than the speed of light. And so the analogy I always use is, take a balloon, if you will. You got a balloon, you paint a bunch of dots on it. As you blow it up, the distance between the dots grows larger. Now, we tend to think that, we tend to take that analogy and view it three-dimensionally, but you got to remember, you're now a being restricted to the surface of the balloon. And even more than that, not only are you restricted to the surface of the balloon, you don't get to see the whole balloon. You only get to see a quarter. And that's probably an overestimate, because it's something probably more on the lines of something the size of the moon and you get to see a quarter. Or maybe it's a $50 or $1. I haven't actually sat down to work through the calculation. So you can see out to the edge of the $50 or the dollar, but the region is just much, much larger, because the region can expand faster than the speed of light, but things can only move through the region at the speed of light.
Okay. And then the other sort of related question is, in sort of the yo-yo theory that you're talking about, where it expands and contracts and expands and contracts, is there, I guess, maybe could you say a little bit more about just the concept of inflation? Because it's basically things that are further away are not only moving faster, but also accelerating. And does that, I guess, under what's, if the universe never collapses back on itself, how could it ever yo-yo back into nothing? Or what could you say about that?
Well, so when you get into these other models, things that are foundational may not be. And so if our universe has no past history except for what may have gotten entirely erased in this bounce, then, if the bounce kind of preserves some information, you now no longer need the inflation to solve some of those problems. And so the bounces are presumably, it grows, it gets very, very large, it collapses back down. And in the process of bouncing, you just get a new cycle. Nobody at this point has a good mechanism, although when you're dealing with these quantum gravity models, one of the ideas that's out there is that, what Hawking and Penrose showed is that under general relativity, things collapse down and you get space-time trajectories crossing and you got infinities. Well, rather than having the space-time trajectories cross, it might behave like a sponge. You can squeeze a sponge for quite a while, but eventually there's a maximum compressibility and then it rebounds. So maybe that quantum gravity era does something like that. But these are a lot of interesting ideas that we don't have the observational tools to test one way or the other.
Okay.
Jeff, I wanted to ask you about the four fundamental forces,
Right.
and how that fits with the universe that we're observing anyway, accelerating. The expansion of the universe is actually accelerating, as Randy just pointed out. And that seems like that would be another force. Is that one of the four forces? And if so, which one?
Well, so as we talk about that, this space energy density is generally the dark energy that we talk about is where this accelerated expansion of the universe, that's the language we use to talk about it, because we don't have a good description of it. Whereas the dark matter, so if you look at the composition of the universe, there's about 4 to 5% of what we know, the energy density, that is normal matter. Stars, electrons, protons, neutrons, all the stuff that anything you've ever thought about talking about, except for dark matter, classifies as normal matter. Then there's this other stuff that we know it's gravitationally there, but it's not normal stuff. And it's about 6 times more than the normal stuff. So you had 4%, 26, 28, or 24%, you get about 28%. The remaining 70-ish% is this stuff called dark energy. What it seems like is actually the most likely characteristic of that is that it's a property of space-time itself. So when you go to a point in space, every point in space has length, width, and height to it. We're all comfortable with that. It actually has length, width, height, and time as well. But the best explanation for this dark energy is that space, not only does it have length, width, height, and time, it also has this property of self-stretching, that in its natural state, it just wants to expand. And so if that's the case, it's not one of the four fundamental interactions, it's the property of space itself that wants it to accelerate or expand and accelerate so that the expansion accelerates. And I think that's the most likely explanation. That's where we're going to end up.
May I ask a question?
Sure.
All right. So in a multidimensional curved space universe, is it possible that all matter, energy, and everything else in the universe is not just running away from itself, but it's also ultimately running towards itself in another great collision or singularity?
So I don't know. Let me take a shot at this and see if this answers your question. I'm trying to wrestle with exactly what that means, because we know that the space between everything is expanding, and that means the distances between any two objects that are not gravitationally bound is growing larger over time. To have a collision, the space between two objects has to get less so that they can collide. Unless the dark energy were to reverse itself and start contracting, which if it's a fundamental property of space, I don't see why that would happen. But the space between stuff will just grow larger and larger and larger over time. And so that's one problem with the oscillating universe models, or any sort of model where you've got an oscillating, some sort of oscillation, is that there's nothing that in our current understanding of physics that would allow it to contract back on itself. Because the dark, like I said, the dark energy is most likely a property of space itself, such that the larger it gets, the faster it wants to grow, and it will never again collide with itself. So I don't think there's.
I'm not talking about an oscillating universe.
Okay, so how do things grow further apart and yet still collide with themselves eventually?
Well, if it's a multidimensional universe, if let's just say I take off from where we are right now, and if I just keep going forever, I end up back at the same place. Okay. If the universe works like that, then wouldn't everything be headed back to a massive collision without oscillating?
Okay, so I can say this, at least in the three large spatial dimensions that we can measure, you can ask the question, what is the geometry of the universe? And in a three-dimensional space, you've got three options. It can be closed like the surface of a globe. So as you move across the surface of a globe, eventually you come back to the point where you are. It could be curved like a donut. There's other ways it could be curved, whether it's simply or complexly connected. There's a whole modern algebra topology that deals with that. But curved and closed is that it comes back on itself. So in principle, if it were closed, everything could come around to the other side and do it. Except that we're not moving away. It's not like there's a center that everything's moving away from and getting there. Everything on that surface is moving away because the surface itself is growing larger. And so now the question you would have to ask is, can you travel through the space faster than it's expanding? And the answer, every point of data that we have at this point says, no, that's not possible, that it's expanding faster than you can move through it. And so you can't get around to the other side. But even more than that, when we make our measurements of what is the geometry, the best we can measure is, sorry, I didn't ever complete my three geometries. One is the closed, the other is open, where as you move further away, things just get further apart. And then the boundary between open and closed is flat. And little bit of geometry that I never did appreciate when I was in high school, but whenever they talk about parallel lines, They always make this statement: parallel lines always remain the same distance apart in a Euclidean geometry. And I never did get the importance of that until I thought about this question, because if you're in a Euclidean, which is a flat geometry, parallel lines always stay the same distance apart. In a closed geometry, parallel lines converge. Think of your globe. At the equator, all the lines of longitude are parallel, but they all converge at the poles. That's a generic feature of closed surfaces, is that parallel lines converge. In open surfaces, parallel lines diverge. The best we can measure is that we live in a flat geometry. Now, the hard part about, or the tough part about that measurement is that your error bars, even if it's exactly flat, your error bars on the low side or on the small side are in the closed geometry, and on the high side are in the open geometry. But we look very, very close to flat. And so in that sense, nothing will ever get back around and collide with itself.
Seems like all those theories, though, presume three-dimensional space.
Well, we do know that we live in that the only dimensions that we are sure exist are the three large spatial dimensions. Now, the question arises, if there are more dimensions of space that are large or even small, what do you do with those? And I imagine you could have some scenarios where what you're saying might happen, but I cannot distinguish. There's no data that points to any of those being good, bad, or other at this point. So, I mean, you're free to talk about it. There's just no observational evidence one way or the other. So,
I don't know how you could observe it. I think it could be theorized, and that's it.
I think that's probably correct. Yeah.
Yes, I was just wondering if anybody was looking into a theory of that sort, because it seems to be the obvious alternative to a pulsating universe.
Yeah, I'm sure there are people that have looked at stuff like that. There are people that are looking at 4 and 5 dimensional gravity. I mean, there's a long history of ideas that people have looked into, and I'm sure that's been one of them. I just don't know what the actual conclusions or what that research showed.
I'd be very interested. I've never heard anything about it. I can't believe it's my own.
Yeah, you might have to go back and look for research that's being published in the 70s and 80s is probably the most likely place you're going to find any research about that. It's not something I hear too much about today.
Jeff, I have one more question.
Yes.
And that is, what is a magnetic monopole?
So a magnetic monopole, I think the simplest way to talk about it is you ask, you know what an electron is, right? So it's a point particle that has a negative charge. It's an electric monopole. A magnetic monopole is a magnet that only has one pole on it. Every magnet you see has a north and south pole to it. We can glue things together and make weird looking magnets, but any natural magnet has a north and a south pole to it. And so a magnetic monopole would be a magnetic charge effectively. And we don't have any, I will say we don't have any evidence that those exist. There is one experiment back in the 70s that was performed at Stanford that looks like a magnetic monopole passed through it, but nobody's been able to reproduce it. And the odds of just happening to get it right the first time are a little bit slim. Nobody has refuted it or explained it away, but it's also not been replicated. And so most people don't think it was actually a magnetic monopole.
Yeah, got one more question. Coming back to this inflation theory, the bigger picture. So in the beginning, there was a big bang, and so the universe expanded very fast, faster than the speed of light. We don't know how fast, but maybe 100 times the speed of light, whatever, okay? And then it cooled down, right? It settled down. And then that model says that when it settled down, then you got these localized bubble universes forming.
So let me.
Is that correct?
There's a little bit of an inaccuracy. So let me fix that, and then we can talk. Okay. So the idea is you've got this stuff that rapidly inflates.
Right.
And it's not just that it's very fast, it's that whatever time frame you're talking about, say, this in this bit of time, it doubles in size. And then in that same bit of time, it doubles in size again and again and again and again. So it's an exponential growth. And so that stuff just expands very rapidly, and it will decay to something closer to the ground state. And that bubble where it's decayed, all the energy of that field that was going very fast goes into heating up that bubble. And that bubble, that boundary of that bubble now is what we would term the Big Bang. And so that it gets really hot because all of the energy that was in the inflation field gets dumped into heating up the universe. And so now you've got a very hot universe that is expanding, but at a much slower rate, and it's cooling off from this very, very hot, dense state now.
Okay. So then you showed a picture where you had all of these different localized universes, right?
Right.
Can't talk to each other because they're bound by the event horizon within itself. Is that correct?
Yes, they cannot talk to each other.
Okay, so, but what is the mechanism for these different universes to cool down? What is, it's not a condensation or anything. Usually in condensation, you have some nuclei, right, that condenses. What causes all of these different bubbles to form?
It's just a process of when things are at a higher energy state, they can decay, things move to the ground state. That's the natural course of things. Occasionally in various regions, this inflation field will decay to its closer to the ground state. And where it'll happen here and then over there and then over there, it's not like they're communicating and talking. It's just a natural inclination. It's just a natural process to go from this higher energy state and to decay to a lower energy state.
Right, but there's no reason why it should decay into 100 little clusters or 1,000 little clusters. Maybe it would decay into just one cluster.
No, it can't decay into just one cluster, because if this region decays and this region decays, you think, okay, they're only a little bit apart. They're going to start expanding slowly inside, but the space between them is still inflating. And so when they start decaying, the distance between them is just going to grow rapidly over time.
Okay, so that's the theory. And so all of these different localized universes, that's what they mean by multiverse. That's new big picture multiverse.
Well, that's one way of defining that's the level 2 multiverse.
Okay, that's a level 2, right?
Right.
And then in the level 2 multiverse, we live in one of these universes. Okay, and in that universe, we have our laws of gravity and everything,
right?
Fine-tuned and everything. What about the other universes? That's decaying a different bubble. What kind of physics are in there?
So the idea that we have is that the laws of this quantum gravity or theory of everything or whatever we're going to call it, that governs all of this space. As it decays or as it gets cooler in our universe, the gravitational and strong or grand unified force broke off or separated. That symmetry was broken, and then the strong nuclear force separated. Then eventually the weak and the electromagnetic force separated. And maybe if the universe cools much more, it'll separate into some others that we just don't know. But presumably that process is going on in these other realms as well. What is true is that the process of cooling down will cause those symmetry breakings to happen, but you can't always, it's not like, I want to say this carefully. We don't know what it's going to look like in those other universes. It could be like you balance a pencil on a tip. It could fall away from, toward, to the right or left, or anywhere in a 360-degree circle. All of those are legitimate. And if I do it multiple times, I'm going to get I'm just going to sample that entire space. So it could be all the different ways that it could cool down and the laws of, or the lower energy laws separate out. You get that scattered throughout the multiverse. Or it could be by some mechanism we don't know, it actually happens this way. This is the only way it can happen. And so everywhere in the multiverse looks exactly like our universe. This is one problem with the multiverse as a scientific theory at this point, is that if you want it to sample all the possible alternatives, it will. If you want it to only everything looks like ours, it will. What you put into the multiverse is what you get out of it. And so we have no way of actually going and looking at these other bubbles and figuring out what's correct.
Okay.
And so the way I say it is that I do think we can determine whether a multiverse exists. I don't think we can determine what the multiverse actually looks like, what these other bubble realms look like, because we can never make any measurements that will tell us.
Yeah, I had a similar question to John's. So the theory is that perhaps when the symmetry breaks in these other universes, it'll lead to a completely different set of fundamental particles.
Yeah, or it could be gravity could be stronger or weaker, or the speed of light's different, or who knows? You know, that's the idea.
Yeah, but it's pretty hand wavy, it sounds like.
Well, it's a reasonable way to look at it, but
yeah,
we have no data that backs that up one way or the other.
Right.
Yeah. So, but we do know in the universe that we live in, let's say universe number one, is fine-tuned. If any of those physical constants change, you know, the universe is going to collapse, not going to exist, correct?
It will be inhospitable to life in one way or the other, yes.
Well, it probably won't exist even, right? I mean, it may even collapse, right? So that's a possibility, right? That's what Hugh Ross says.
Well, it'll either collapse or grow so rapidly that nothing will form. Those are
okay. Okay, so that same possibility should apply to the other universe, universe 2, universe 3.
Right.
They have to be fine-tuned if they're going to be existing, right? Otherwise, they can't exist.
So if you were able to look at the distribution as a whole, yes, you're going to find some that just expand very rapidly, some that collapse very quickly, and some distribution, presumably, where our universe falls somewhere in that distribution. But again, that's what we think, but we have no way of measuring whether that's actually true or not.
Yeah, of course.
And in fact, there was a very, I thought a pretty profound paper is by George Ellis, who's a scientist, I think down in South Africa, who's basically, his argument was we need to be very careful with the multiverse because what you put into it is what you get out of it. And that's not it's not that it's not a reasonable idea, but there are physics and science is littered with ideas that seem reasonable and just were outright wrong. And so just because it seems reasonable doesn't mean it's actually correct. And so we need to be careful there.
Okay. All right. Thank you.
Yeah. Great questions.
Well, you've stretched my mind a lot. Are there any other, does anybody else have any questions they want to raise at this time? I don't want to shut things down too quickly, but we've been going at it for a while now. Jeff, could I ask you to close the meeting with a word of prayer?
Sure, we'll do that. And, I just kind of in wrapping up, one of the things that I have learned in this process of being challenged about whether there's a beginning is just recognizing how much effort has been put into showing that the universe doesn't have a beginning. And because of that effort is why the evidence for the beginning is so strong. And it has really given me a great confidence that what Scripture says, whether I understand it, whether challenges are raised that I can answer, I am very, very confident that the Scripture will ultimately show itself reliable because God himself is that reliable. And so I've learned to just not fear a lot of these questions, even though I may go for a year or better without a good answer to them. And so, just encourage you to have confidence that God is reliable and none of these challenges are new. or the idea of getting challenged is new, but Christianity and Scripture and God have withstood the test of time, and they will continue to do so. So let's pray. Heavenly Father, thanks for this time tonight. It's been fun just to talk, and these are great questions, and just a joy to think about the creation you've given us to live in and the questions you've given us to ask, and just the majesty and awe and splendor of your creation, as well as its understandability and how much it points to you. Lord, help us to be more confident in the truth of Christianity, that we might go tell others about you and your love for them. Lord, we love you and thank you. In Jesus' name, amen.